sum of the forces, but we're missing one, and we knew the forces all added up to 0, we could solve for it. This semester, we're going to try to identify the forces. If we know all of them, we can figure out the acceleration. So we're going to use F equals ma. The acceleration will often be an unknown. One very common goal is you've designed some contraption. Maybe it's complicated, maybe it involves gears and pistons and who knows what. And you're going to identify all the forces acting on your contraption, and you want to figure out what is my contraption going to do. So, in other words, what's its velocity going to be as a function of time? Is it going to speed up? Is it going to just sit there? What's going to happen to it? So often we'll try to identify the forces, use the forces to figure out the acceleration, and then use the acceleration to figure out velocity, use the velocity to figure out positions. So what we're doing here in the first week and a half of the semester is temporarily forgetting about the forces, or for the most part. So some of the homework questions they would give you the force, but it was only they would give you the force and the mass. All you had to do was divide to get the acceleration. So we're not doing anything complicated with forces yet. We're just trying to see if I give you acceleration, can you get velocity and position and vice versa. We've done some examples in class. The easiest example that we did, the first one we did, was we were given position as a function of time, and then we used that to get velocity and acceleration. That was the easiest situation. Unfortunately, it's not the most common. As I said, we're usually going to use forces to get acceleration. So we're not often starting with position. So given position, can we get velocity and acceleration? The answer is yes. What do I do? Well, velocity is dx dt, so I just take a derivative and I get velocity. Acceleration is dv dt, so I just take a derivative and I get acceleration. I'm not going to do another example with that. That's the easiest situation. Another example, suppose we're given acceleration as a function of time. If I'm given acceleration as a function of time, we did an example last class trying to get velocity and position from that. That was a little bit trickier because if you're given acceleration, you had to set it up as a differential equation. If you're given the acceleration, you'd have to write a equals dv dt. And if the acceleration is given as a function of time, that's what that parentheses t means. So the acceleration is presented, and the variable in it is a t for time. If the variable is a t for time, it's not too hard to separate this differential equation. What we mean by separate is I need to get all the time variables on one side and all the velocity variables on the other. What should I do for this to get all the time variables to one side and the velocity variables on the other?
Multiply both sides by dt.
Multiply by dt. So I get a is a function of t, dt equals dv. Then I integrate both sides. I will probably need some initial conditions in order to solve it. In other words, I'll need to know the velocity when time is equal to 0. I'll need to know the position when time is equal to 0. Because when I do these integrals, if I didn't have any limits to put on there, I'd have a plus c at the end, and I'd know how fast it was going, plus or minus some constant. That, of course, doesn't help you very much. The police officer pulls you aside and says, you were going 300 miles an hour, plus or minus some constant. Well, kind of the devil's in that constant. So if we don't have the initial conditions, then you would not be able to get definitive numbers for velocity and position. There was a problem you had on the computer exercise, which we've only spent maybe a total of 10 minutes on, 5 minutes one class and 5 minutes on another. But there's a problem where I give you a graph of velocity versus time, and I ask you randomly several different questions. So if you're given a graph of a particle's velocity versus time, and I need to find the acceleration, what do I do? versus time, and I need to find velocity. What do I do? If I'm given a graph of velocity versus time, and I want to find the velocity at a particular time, what do I do?
You just look at the point. Yeah.
I just read it off the graph.
Yeah.
So if I'm given velocity versus time graph, and I want to find the velocity, just read it right off the graph. Because that's what it is. It's telling you the velocity at every time. If I'm given a velocity versus time graph, and given no initial conditions, and you're asked to find the position at a particular time, the answer there is that question mark. Because you can't do it. If you're not given an initial condition, you're only told the velocity is a function of time, you don't know where you are. You don't have any starting point. So therefore you can't figure it out. Okay, so if you're given acceleration as a function of time, you have to set up this differential equation, which isn't too hard to solve, multiplied by dt, and then we can solve it. What I'm going to do at the beginning of class today is overview the different possible kinds of problems you might get. It is not my goal to do a particular example for this. I did an example for this last class. I'm trying to overview all the different cases, and then maybe we'll pick some of the harder cases and do an example from those. Okay, so one possibility is you're given position as a function of time. That's easy. Take derivatives. Another possibility is we're given acceleration as a function of time. That's still not too bad, but we have to get all the t's to one side, all the v's to the other, integrate both sides. That'll give me velocity. So that'll give me velocity as a function of time. And then I can repeat to get position as a function of time. Okay, next possibility. Given velocity as a function of time. So we're given the velocity as a function of time. We want to get acceleration and want to get position. If I'm given velocity as a function of time, what do I do to get acceleration?
Take the derivative.
Take derivative. That's easy. What do I do to get the position?
Integrate.
Integral. Same procedure we had over here. Okay, so for here, I'll put a star because we're doing the same thing we would have done over here. And for this step here, I'll put a box. No. Put the box here and say that we would do the box procedure. Because if we're given velocity to get acceleration, I would take a derivative. So that's the same thing. Given velocity to get the acceleration, I would take a derivative. What other possibilities are there? Given acceleration as a function of velocity. So instead of being told the acceleration and how it changes with time, I can be told the acceleration and how it changes with velocity. And we're trying to figure out velocity and position. So if I'm given acceleration as a function of velocity, let's see what we might do. We'll of course write acceleration dv dt. If you claim you're stuck and haven't tried that, then it's like, oh, I don't know what to do. That's what this first part of the course is all about. Acceleration is dv dt, and velocity is dx dt. So if you're stuck and you haven't tried one of those two things, then try one of those two things. So we've got acceleration as a function of velocity equals dv dt. This terminology means I'm not going to have a variable t in there also. Now I need to try to separate this. What should I do to try to separate this? Someone besides Roger.
Multiply both sides by dt and then divide by av.
Okay, and the way you'd say that is not a times v, it's a as a function of v. So this a as a function of v could be something like a is equal to 2 sine 5v plus 4. Could be. It's just some example. It's some acceleration given to you with a variable v in it. So by writing a as a function of v, I'm not claiming what that is yet. I'm just saying it could be something like that. And the procedure would be the same then. To separate it, we'd multiply by dt and then divide by the a as a function of velocity. And then this side of the equation should have only velocities in it. That side of the equation should have only t's in it. Then we would integrate both sides. We would need some initial conditions. And that would then result in some velocity as a function of time. Because I'd have v's and t's only. Now, to get from velocity as a function of time to position as a function of time, this is the other thing that might be asked. To go from velocity as a function of time to position as a function of time, velocity to position, I do the star. It's the same thing. Now, is that star easy to do necessarily? No. This might involve an integral. Anytime there's an integral involved, nothing is necessarily easy. It just depends on which integral is it. Okay, other possibilities. Let's try, given v as a function of x, so the velocity could be given to us in terms of position. And I'm running out of combinations. What's the only remaining possibility for acceleration? How could acceleration be presented? I've already talked about acceleration as a function of time and acceleration as a function of velocity.
Position.
What else remains?
X.
Yep. So I need to figure out a procedure for these last two. I suppose I can tack on to here, given something like v as a function of a. Velocity is provided in terms of acceleration. This is not really a new thing, though. Let me show you why. Suppose we're given v is equal to 2a squared. I can rearrange this as v over 2 equals a squared, or a is equal to the square root of v over 2. So if I rearrange v as a function of a, I can untangle it and make it a as a function of v. Do I already have a column for how to handle a as a function of v? Yes. Okay. So if I have v as a function of a, you might think, well, that's a new combination. I haven't talked about it. Well, actually, we have. V as a function of a, you can try to untangle it, and then that gets you into this column over here. Doesn't mean the math is going to be easy. So if v were equal to 3 sine a, then a is equal to inverse sine of v over 2. So I'd be having to go through this whole problem dealing with integrals of inverse sines. Yuck, right? Okay, so depending on what these functions might be, the procedure might be really ugly, but you can still do the procedure. And for those of you, most of you had me for Engineering 110, and the engineering programming class, one topic we worked on was how to solve an integral. So I agree, you may have forgotten, but in that class we set up programs that would solve an integral for us. And the procedure for solving the integral with the Engineering 110 class was no harder depending on what the integral was. You may have had some difficulty setting it up. So the integral of x dx was as difficult as the integral of inverse arctangent divided by sine secant and blah, blah, blah. It didn't make a difference. Once you set up the program, it was equally easy to integrate one thing versus another. So if we get stuck on some of these, maybe most of the problems today on today's quiz, and many of the problems are rigged. The formulas are simple enough that they do work out to be integrals that are doable.